Hi, everyone. Thank you to Yanni and Matt and the QC Ware team for the opportunity to be here again this year. It's always impressive to see the rate of growth of quantum as an industry, and I think this conference is a great indicator of that and a good way to track it. So I'm going to tell you a little bit today about Rigetti, and for those of you who are on Twitter, please follow me so I can follow you back. I really like to stay in touch with the quantum community on Twitter and appreciate the really good vibes there, so thank you. Here's the outline for today. For those of you who are new to Rigetti and might be a little bit new to quantum computing, I'll give you an intro to what we do and our approach. I'm going to tell you a few updates on hardware, including our new Aspen 7 32-qubit system. Then a bit of an interlude on algorithms and some of the ways in which we're leveraging our quantum classical hybrid computing system to unlock new and potentially powerful programming frameworks based on ML. And then an update on some of the physical 2-qubit gates on our systems that are now available over our Quantum Cloud Services platform. And then I'm going to offer a few kind of editorial closing remarks on the path forward, not just for Rigetti, but for the overall industry and the march towards kind of unlocking the potential and value of quantum computing. So at Rigetti, we are what we call a kind of fab-first or a fab-driven full-stack quantum computing systems company. And we focus from the chip out. So my background is in superconducting qubits and in specifically doing fab and design of superconducting qubits. And that is the kind of core central activity that organizes our effort at Rigetti. So we have kind of the only US-based dedicated quantum fab for superconducting qubits to our knowledge. We build these superconducting qubit-based chips and we drive the innovation cycle of improvements at the qubit level through that fab capability. We integrate those chips into a full-stack computing system that focuses on hybrid quantum classical integration to unlock the capabilities for near-term NISQ-era machines and devices. Those full-stack systems include both working from the chip out, kind of significant packaging effort, cryo-RF, control systems, to build a full quantum processor unit, and then also baseline level of integration to deliver access to those machines over the cloud. Then we also do innovation and work on quantum algorithms and applications and work with customers backwards to identify what kind of, through our customer engagements, what kind of capabilities they need to help support them with workforce development, application development, and full stack prototyping of applications on quantum computing today. So the core, as I said, the kind of core of Rigetti's capabilities centers around semiconductor style, but manufacturing of superconducting qubit-based chips. This is an image a few years old now of our fab, which is across the bay in Fremont, or a few miles away in Fremont. And what we do is we've built up this capability that is focused not on volume manufacturing. Manufacturing and fab of superconducting qubits is not about scale. It doesn't have the same economics of traditional chip manufacturing. It's about kind of shortening the learning loops, shortening the innovation cycles, and accelerating the progress on building ever more reliable and higher performance qubits and more of them over time. And so what we do is we operate this facility in a very kind of short loop methodology or framework where we do design fab test cycles as rapidly as possible. And we couple to that obviously a significant effort on design tools, allow us to design these chips as quickly as possible. To do more advanced electromagnetic simulation to get the parameters of the chips right. And ultimately the fab kind of sits at the center of effort. Now I want to kind of talk a little bit about why I think and why I believe and the company believes that a US-based manufacturing capability is very important going forward. Ultimately, the economics of quantum computing is going to be very different than the economics of traditional computing. And much of that, and it's going to be a game of rapid innovation going forward. And as I said, it's not going to be about scaled volume manufacturing. It is also not about reducing feature sizes. It's about very hard intellectual work that centers on material science, removing defects, the ability to characterize in a quantum environment the chips that you're producing through your fab process. And that tight integration is absolutely essential for progress going forward. I fundamentally do not believe that existing semiconductor manufacturing capabilities are going to be able to be repurposed to solve the core problems in driving innovation going forward in quantum computing. There are going to be new facilities dedicated and purpose-built for solving these specific problems, and we think it's absolutely essential that America is the leader in the innovation and the manufacturing of these chips going forward. So we have made that investment. We have been running this fab for about 2 years. We built it starting 3 years ago. And we think it's an essential kind of component of our strategy going forward. So the chips are kind of the core, the hard thing about building quantum computers today. But the chips alone do not compute. You need to integrate them into a computing an environment where their quantum performance can be exploited, or the quantum behavior can be exploited. These are superconducting qubit-based chips, which are operated in a dilution refrigerator. This is in the foreground here is a picture of the system that contains our current, or akin to the one that contains our current Aspen 7 chip that I'll tell you about shortly. This is our quantum computing facility that is in Berkeley, California. We've got 8 different quantum computing systems that are used for a combination of both trial deployments for customers to enable algorithm and application testing and development, but also just for short loop testing and characterization of the quantum performance of our chips. It is impossible to do the rapid innovation and to drive the progress that is needed in quantum computing without trial and error and without exploratory development. And so much of the capability that we have is allocated towards that innovation. And the ability to tightly couple quantum characterization with the fab is a core capability and a core strength that we focus on at Rigetti. So as I said, we also offer access to these machines over the cloud, and we've been doing so for about 2 years over a platform called Quantum Cloud Services. Quantum Cloud Services has been, we have users and partners and customers from 10 global Fortune 500 companies. Our particular emphasis and focus that we have chosen is in finance and the energy industry, as well as in the defense industry and government. We think that there's significant opportunities there, and we have specific organizational expertise in those areas. So if you're in finance or the energy industry, we'd love to talk with you and learn from you about what your needs and requirements are. We also work with some of the, there's a very large cohort of really great application companies that have come into being over the past 3 years in quantum computing, and we work with many of them to design and develop algorithms and applications built on top of the Rigetti platform. We also work with academic research partners who are doing more core algorithm research rather than just application development. And we work with many of the national labs as partners as well. So Rigetti QCS is the fastest hybrid performance, has the fastest hybrid performance in the industry. And what that means is we have focused on tight integration of quantum processors with classical computing to optimize the performance of variational algorithms in near-term NISQ-era machines and devices. The investment we've made there has enabled significant advances in algorithms that I'm going to talk about going forward in the presentation. We have also strategically decided to enable a very low level of access for algorithm development and research within the stack, so people can directly play with new 2-qubit gates, which we'll also talk about today. And we also expect to continue to do this to facilitate quantum error correction research going forward. We've reached a moment where quantum computing, the first kind of inflection point, I think, happened a couple of years ago where people could empirically start developing new algorithms and start testing new ideas. And I think we're going to see over the next couple of years the results of some of that acceleration. I believe that we're on the cusp of quantum error correction becoming also an empirical kind of experimental field of research, and that is essential to driving the improvements in quantum error correcting codes and fault-tolerant frameworks that is needed to achieve the potential of quantum computing over the very long term. And so our platform is designed to enable that research. So the most recent, we have deployed, I believe, 6 different systems over time onto QCS for certain periods. The current system that's available is both a 16Q system, but also this week last week we announced that the first Rigetti 32-qubit system called Aspen 7 is available. I believe this will be available on QCS Monday of next week. So it's currently integrated. This machine represents a significant step forward over the past 12 months for the company. We've been able to increase our T1s by 7x since 12 months ago for the deployed systems. We've been able to increase our T2s by a factor of 10 since 12 months ago for the deployed systems, while doubling the number of qubits and also reducing the error rates in our 2-qubit gates by a factor of 2. So the reason I'm giving you all those stats is because it's indicative of the rate of progress on this technology and how fast the hardware is getting better. And people need to be connected to the hardware to enable and to be aware of those advancements and to be able to start to unlock the performance that quantum computing is starting to be able to achieve. We also have active reset enabled on the platform, and this is a significant component of the overall application level performance that we're able to deliver for hybrid algorithms. As your coherence times get longer and longer, you don't want to wait for the qubits to relax down to the ground state to restart to run another shot on the quantum processing unit. So we have enabled active reset, which allows you to run algorithms very fast. Effectively, you run the gate depth that you want to run, whether it's 5, 10, or 20 gates, and then are able to reset the qubits back to their ground state. On the Aspen 7 system, there are some qubits whose T1s are above 100 microseconds. So effectively, this increases the shot cycle time by roughly a factor of 10 that you would have relative to active reset not being available. And then last week, we're also very excited to be a part of the recent AWS announcement of the Bracket quantum computing service on AWS. And the Rigetti 32-qubit system is currently integrated with Bracket and will be available for users soon when Bracket is opened up. So we're in the NISQ era of quantum computing, and in the NISQ era, there are really kind of two pillars of what we call the kind of two major hybrid algorithms that are of interest for potential applications in this NISQ era. Those are VQE and quantum approximate optimization algorithm, or QAOA. So I think of these in a simple way. VQE is what you use if you're trying to solve an intrinsically quantum mechanical problem. If you want to calculate the ground state energy of a molecule or another physical system that is implicitly quantum mechanical. QAOA is a hybrid algorithm that you can use if you want to use quantum computing to solve a problem associated to classical data or to a classical network or a classical graph. And these two algorithms are similar. They're not the same, but they're very similar, and they share a common foundation. And ultimately, in both cases, what you do is you encode a problem into a Hamiltonian. You select a parameterized ansatz, say U of X, that you believe solves minimizes an energy or solves a problem with respect to that Hamiltonian. You pick an initial X, you prepare some states and estimate the energy H of X. And ultimately, you then put that into a classical optimization loop, and you run that in what we call the variational loop. So estimating H of X is the only part of this variational loop that needs to take place on your quantum processor. Given this framework, it becomes very important to offer an overall system that allows you to run that variational loop with a low level of latency, high speed, and high accuracy. And so at Rigetti, we focused on building our systems to optimize the performance of this variational loop. Now, over the past year, there's been, based on some of the platform capability that we've been able to enable within the market and users of QCS, people have started to expand upon basic VQE and QAOA. And in the past year or so, this has really started to accelerate. So ultimately, in both of these cases, what you're doing is solving some sort of linear algebra problem. And work has been done over the past year or so to start to broaden the generality of that linear algebra problem. They are still relatively specific in special cases, but the generality is increasing year over year in a pretty significant way. This is an exciting example, I think, indicative of this trend that was done by Patrick Coles and his team recently, where they used a Rigetti system over quantum cloud services to solve a 32 by 32 system of linear equations. And ultimately, that 32 by 32 system of linear equations was solved on a 5-qubit lattice on QCS. So it's exploiting the exponential dimensionality of Hilbert space in a 5-qubit system to get 2 to the 5 by 2 to the 5. And ultimately, this is a generalization of effectively VQE called the variational quantum linear solver. It is different, but it draws upon the same kind of variational loop. And ultimately what you do is variationally minimize the overlap between a vector B and A times X. Ultimately, what was found in this is that the algorithm showed significant resilience to noise, and also is able to run with fixed depth with respect to the size, the size of the linear system. So this is still a special case, and the operator A that was used in this paper is one that is generally directly decomposable into poly operators. And so there's follow-on work that needs to happen to make this ever more broad in general. But we have an indication, and we have some steps that have been made in terms of going beyond chemistry problems and going beyond classical optimization problems to solving more generic kind of computational primitives. And progress that is made in solving systems of linear equations has a kind of an immediate application across many different industries and application areas. And so it's a very exciting direction from our perspective, and we encourage further work in this direction. So congratulations to Patrick Coles and the team that did this. So one of the questions we've asked in the past year is we've made a lot of investment in optimizing the performance of this variational loop. What other programming frameworks or what other approaches to algorithm design might that enable? And we asked a kind of an interesting and fun question: can machine learning help design better hybrid algorithms? And specifically what we mean is, can machine learning potentially design a better ansatz for a variational algorithm than what we design based on human knowledge or human intuition? And can that ansatz potentially be made aware of the specific noise of the specific quantum, the specific chip that you're running on at that point in time? And so ultimately what we did was we used some very interesting and exciting tools that have been built by OpenAI for building a reinforcement learning agent. And we trained that reinforcement, we basically hooked that reinforcement learning agent up to one of our quantum computers. And we trained it to solve a combinatorial optimization problem. A 10 node graph QAOA across a few different instances of optimization problems from max cut, max QP, and a Kubo problem. So what's shown in the data here is indicative of the promise or the potential of this approach. The gray data is the trained agent. The red data is the untrained agent. And blue, we're using the quantum approximate optimization algorithm as the benchmark. So QAOA represents the best known human designed algorithm to solve this problem on a quantum computer. And what you see is that in the noiseless simulator, QAOA outperforms the untrained agent, but underperforms the trained agent. So we're able to get a performance boost by doing the reinforcement learning and training the agent to produce the quantum circuit that solves the problem. Now, when we went to run that on the real quantum computer, what we did was train it on a noiseless simulator and then finish the training in the presence of the noise of the real device. And what we saw was that the performance of QAOA relative to the trained agent, that gap actually broadened. So effectively, the agent was able to train around the noise and to learn good representations of the problem, in the presence of noise, so that the performance on the noiseless simulator relative to on the QPU, the difference was minimized. And this is a really exciting direction. It's absolutely a proof of concept, but we believe that there's real opportunity, especially as we start to reach a supremacy number of qubits and well beyond, to leverage reinforcement learning and other methodologies to do advanced programming of these chips beyond the kind of heuristics and frameworks that we know of today. So I want to talk a little bit about physical 2-qubit gates. So the challenge in the NISQ era, and this is what we work on every day at Rigetti, the challenge in the NISQ era is building machines with enough qubits and with low enough noise to solve useful problems. And there's two different ways that you can kind of push on improving the computational capabilities of a quantum computer with respect to noise. You can decrease the physical error rates, or you can decrease the number of gates you need to run to obtain a computational solution. And the framework of universal quantum computing hinges upon a basic notion that you need a universal set of gates that include at least a pi half rotation as a 2-qubit gate to be able to implement and decompose any algorithm into that set of universal gates. So our team asked an interesting question: What if we delivered an over-complete universal set of gates? What if we delivered more 2-qubit gates than are needed to have a universal set? How might that impact the gate depth that you're able to, the gate depth of a compiled circuit on your machine? And a simple example is shown on the left of the slide here. A swap gate, which swaps the state of 2 qubits, can be compiled into 3 controlled phase rotations or 3 I-swap gates. But it could be also compiled down into 1 I-swap and 1 CZ, effectively reducing by a factor of a third, by 33%, the number of 2-qubit gates in your circuit. Swap gates are essential, especially for superconducting qubit-based systems that use a nearest neighbor coupling that we think is going to be an essential component of any large-scale quantum computer. It will require nearest neighbor coupling to control errors. But with swap gates, you can move data around a chip and effectively swap qubit states so that you can represent an all-to-all connected lattice if you have swap gates in your system with low overhead. So ultimately, what we found was that it does pay to have both controlled phase and I-swap gates available physically in the hardware of your system, and that's what the team developed. So XY gates effectively swap the quantum states of this XY family of gates, or XY theta, does a controlled rotation by an angle of theta between the quantum states of 2 qubits. We're able to tune up this family of gates with between 96 and 99% fidelity, where your variance is with the specific angle of the XY theta rotation. These gates today are available on the Aspen 4 system on Quantum Cloud Services. So I want to give an example of how that can help solve problems with a lower gate depth. So a specific example is a 4-node optimization problem where we're solving a max cut problem using the quantum approximate optimization algorithm. If the graph that you're solving is a linear chain connected with circular boundary conditions, so effectively a square, you need 8 C0s to represent the algorithm. Those 8 C0s in physical space could be compiled down into 10 CZs, or they could be compiled down into 6 CZs and 2 I-swaps. So if you have I-swaps, you can match exactly what you need to run it if the physical lattice matches the connectivity of your graph. In an all-to-all connected lattice, it requires 12 C0s, even if you have an all-to-all connected superconducting or quantum processor. And effectively, what you're able to do when you have access to both the CZ gates and the I-swap gates is to match that minimum number of gates of 12 for an all-to-all connected lattice in your physical architecture, even though your physical architecture is nearest neighbor coupled. And so ultimately, what this gives you is constant or no overhead compilation for an all-to-all connected problem. This is very important, and actually, these XY theta gates are also very interesting for optimization problems where you need to conserve the number of excitations in a problem. If you think of a traveling salesman kind of problem, you need to visit each city once, and that city would be represented as a spin-up or a 1 in your data set. And so you want to conserve the number of excitations in the system, and these XY gates do that. And so they're very interesting for combinatorial optimization problems. And it's an exciting direction going forward. So at Rigetti, we are focused on delivering quantum computers that unlock useful, running real useful problems as soon as possible. We also recognize that quantum computing and everyone who is in it is absolutely in it or needs to be in it for the long game. And part of the long game means setting up a foundation for scaling and for driving iterative improvements in the number of qubits, driving down the error rates and improving the overall performance of the computational systems year over year for the very long term. We have invested a significant amount of energy and time and capital in developing a scalable platform for our quantum computing systems, and that is the foundation of our Aspen 7 machine, which was recently released. Our cryogenic platform, one of the major advancements we've been able to do is replace the coaxial cables in our systems and all the individual filters and connectors with a flexible PCB platform that reduces cost significantly, reduces complexity, and increases the reliability of these systems because it reduces the total part count and the number of failure modes. Into this flex PCB platform, we've also been able to integrated attenuators and filters that significantly simplify the overall system and positions us to scale the number of qubits significantly going forward. We've also developed an electronics platform that we're now on our 2nd generation of, called Tsunami. The Aspen 7 system is based on Tsunami 2 control system that includes direct digital synthesis of microwave signals for controlling the qubits, as well as FPGA logic in a very fast feedback, low latency architecture that addresses the concurrent requirements of both NISQ-era hybrid algorithms and quantum error correction with low latency feedback and control. We also have several research and development improvements in the pipeline, and last year at this conference we talked about having achieved 100 microseconds of coherence time for the first time. On the left of the slide, we run coherence monitors and coherence chips continually through our fab and are always innovating, making process adjustments to improve it. So over the past year and a half, we've shown significant progress going from red to blue to green on the coherence of those devices, and over the next 12 months I expect that these coherence improvements will continue to migrate from our research and development chips into our production chips. We've also made significant progress on addressing another major physical source of error within superconducting qubit-based systems and all quantum computing systems, in fact, and that is crosstalk. So our architecture now includes superconducting vias in the quantum integrated circuits and superconducting and a superconducting cap that is bonded with superconducting bond onto that quantum IC. With that architecture, we've been able to reduce the crosstalk to below that, around that 0.1% level at both DC and RF. And this is below the threshold that we think it needs to be to achieve 3 nines of fidelity in our platform going forward. So I want to talk a little bit about the path ahead. And in the era we're in now, quantum computers we've had the first demonstration of supremacy, and congratulations to the incredible achievement of that. We have, there's multiple different modalities of quantum computers that are pursuing the kind of, the commercial opportunities at this moment in the near-term future. We're all in this for the long game. And the path to unlocking the long-term value of quantum computing for the world and for the United States is, at the other end of a long and arduous path to full fault tolerance. And that has been our focus at Rigetti from day one. But let's just talk about what is required to really get there. First of all, this is a set of necessary requirements. It is by no means sufficient. There needs to be large increases in qubit counts by several orders of magnitude. In order to do that, the per qubit yield has to increase with the number of qubits. If you produce we could produce a chip with 1,000 or 10,000 qubits on it, unless your yields are increasing by the same fraction, the chip is not going to work. And so the per qubit yield needs to increase significantly as we scale. The per edge yield, or the per 2 qubit gate yield, needs to increase significantly as you scale as well. Those yield factors are as important as the performance factors, and they need to happen at the same time as significant improvements in performance. So we need to reduce error rates in physical 2 qubit gates by at least 1 order of magnitude, probably maybe 2 orders of magnitude going forward. In order to do all of that, we're also going to have to drive significant reduction in the overall cost per qubit. And then the other thing that is needed is there are absolutely large improvements in quantum error correcting code performance needed to truly unlock fault tolerance. The surface code approach with magic state distillation, or potentially some recent developments that may allow us to avoid that, is a proof of concept. In no way, shape, or form do I believe that that's actually going to work at scale. There needs to be significant improvements in quantum error correcting codes in order to really unlock this. We need far lower overhead than the known codes that we have. We need simple and accessible frameworks for developing and testing new codes. And quantum error correction needs to become an empirical field and an experimental one, hand in hand with the folks building the hardware and building the systems, not a theoretical study. And low-level access to NIST systems, I believe, can really be something that helps accelerate this path towards fault tolerance, which is ultimately why we're all here and what we all want to achieve in the long term. So thank you so much for your attention, and I welcome questions.
Hi, thank you for the talk. I was wondering, what is a dollar amount, $ sign per qubit today?
Maybe come talk to me after.
Okay.
You said that you used the variational. Could you elaborate on that?
So yeah, I encourage you to reach out to Patrick Coles and the team that did this. It was implemented on our platform on a 5-qubit lattice. Effectively, you're variationally optimizing the overlap between a quantum operator A and the vector that that diagonalizes that. And it's a generalization, effectively, of variational quantum eigensolver, or an adaptation of it, or it comes from the same kind of kernel of an idea. It's a very exciting direction. It's very early, and we believe it does have the possibility of eventually solving some categories of linear systems where the matrix is decomposable in an efficient manner. And we think there's opportunity there. It's absolutely an early prototype or an early demonstration of the concept of more general linear algebra with quantum computers.
Thanks.
Thank you. That was great. I know we're all here to collaborate and work together and kumbaya and all that, but I'd be interested to hear, how do you have a technical, philosophical difference in your approach to, like, IBM or Google or somebody, some of the other guys? Would you clarify for us how you guys are tackling this in different ways? Is that a fair question?
That's a very fair question. And it's not an easy question. In my view, the vast majority of the resources in the field are going behind an approach that is likely to be have a major role to play in eventual large-scale fault-tolerant quantum computers, and that is superconducting qubits, transmon-style devices, and all the constituent or attendant technology needed to do that. Strategically, we have some differences. We have our own captive foundry, and that fab capability is dedicated for doing exactly what we do. We have emphasized for a long time hybrid integration, which is a unique capability to my knowledge today, and remains so. And our approach also on the customer side has been to work directly with customers and to partner with them to help them understand the applications and algorithms that the applications of quantum computing within their industries and within their businesses. And as a standalone business, I believe that is unique. I think that we're competing with some of the biggest, smartest technology companies in the world, and we fully recognize that. Those people also realize what a good strategy here is, and I think there's been a lot of convergence of that strategy.